Hello everyone. Today we're looking at Le Chatelier's principle. We're going to be stepping away from the math part of equilibrium and looking at some qualitative equilibrium and understanding how we can actually control equilibrium and affect it. So Le Chatelier's principle basically states when a chemical system is disturbed by a change in a property, the system adjusts in a way that opposes the change. Basically what this means is that anything we do to an equilibrium, the equilibrium will try to undo it. So if we add something, it tries to get rid of it. If we heat it, it tries to cool itself. So it's going to always try to undo what we're trying to do to it. It always tries to get its equilibrium back. There are three different things that we're going to look at today in terms of changes that will affect equilibrium, and concentration changes are number one. So a concentration change is just either adding or removing reactants or products. It doesn't matter which. And again, the whole idea is that equilibrium will always try to get itself back. We actually saw an example of this when we did our activity, when we were exchanging those 100 pieces of stuff back and forth, and we took part of them away. That's a concentration change when we do that. So let's have a look at the two examples at the bottom. So the first one is the removal of carbon dioxide. Let's see if we can predict which way the reaction will shift to try to undo what I've done. So imagine that I have removed some CO2. If I take CO2 out, the equilibrium is going to shift to try to make more. So what will happen if I take CO2 out is it will shift to the right to try to make more CO2. Let's have a look at what happens with the addition of water. If I add water, I'm adding to this side of the equilibrium. Again, it's going to try to undo what I've done. So if I add water, the reaction will shift to the left to try to get rid of it. So again, it always tries to undo what we do to it. On a graph, which we'll focus more on tomorrow, we can see a change in concentration because one thing spikes. So in this particular case, we have three ingredients, NO, Cl2, NOCl, but only one of them is actually spiking. This particular spike is an upward spike, which means we have added something. And then in this case, it would be NO. If we had the spike going in the opposite direction, so for instance, let's go down to NOCl, let's say that it did this and then went like that. Again, this sort of spike is a downward spike, which means I've removed something. And you'll notice it's a spike. This is time along the bottom because when I add and remove, it's something that happens quickly. And so it's not something that takes a while. It just happens in a split second and away we go. This is really good for industry because this is one of the ways that we can actually use to manipulate equilibriums. So if we have a look at the example at the bottom here, x2 and y2 in equilibrium with 2xy, if I were constantly dumping reactants into my vessel, the reaction, the equilibrium, will try to get rid of it, which means I make more product. Also, since I'm trying to make more product in the first place and give it to my customers, by removing the product, which I need anyways, again, it continues to shift to the right to try to make more. So this is how industries get around the whole idea of when we're stuck with an equilibrium that doesn't make 100% products, we can use Le Chatelier's principle to force the reaction to do our bidding. All right, number two, the second thing we can do when we're working on Le Chatelier's is temperature changes. Now, these particular changes are only going to affect endo and exo reactions. You'll remember endo and exo from Unit 1. These are things that have an energy associated with them. So not all reactions heat up or cool down, but these particular ones, because they are temperature sensitive, we can use temperature to push the equilibrium around. So if we remove heat, the system's going to shift to try to make more heat. If I add heat, it's going to try to cool it off. It's always going to try to undo what we do. The key to temperature changes is to treat it like concentration. And to do that, we're going to add energy as part of the equilibrium equation, as you'll see. So for instance, this example has N2O4 in equilibrium with 2NO2. we have a colorless solution on the left-hand side and a brown solution on the right-hand side. One of the videos I've posted for you will actually show you this, and we usually do this one in the classroom, so unfortunately you'll have to watch it by video. But this part here is really important. If I were looking at this, the first thing I would have to do to be able to explain this is think about, is this endothermic or exothermic? So this is a positive sign. This means endothermic. And the second thing I want to do is I actually want to include that as part of the reaction. Endothermic, we think of our types or representing enthalpy change. The other way I can show an endothermic is I can add it as a reactant. That's really important because we use this now, again, just like we would with equilibrium or with concentration to work this out. So the first example I'm going to do is a cool. Cool means that I'm going to remove the energy. If the energy is on the left-hand side, then the reaction will go to the left to try to make more. If I heat it, that means I'm going to add energy. And if I put energy in, it's going to shift to the right to try to use it up. So again, it's just like concentration, but the first step is to put the energy as an ingredient so that I know which way to shift, left and right. On a graph, temperature is going to be gradual everywhere. So for instance, I have an example of A and B. Right here, you'll notice there's no spiking. It's all gradual lines because temperature is something that doesn't happen instantaneously. I can't dump temperature in like I can dump a container full of things like concentration, so I can spike it. Temperature is something that's gradual, so I can put something in a hot water bath. It's not instantaneous. It'll take a few seconds to get hot or to get cold. All right, number 3 are gas volume changes. And the reason I have our equation here, C equals N over V, is because this is going to help me understand what's going on. So let's write it out like this, C equals N over V. The first example that we're going to look at is if V is increasing. So think about if I were to increase V, what happens to concentration? Remember, equilibrium is always talking about concentration. This means that the concentration is going to decrease. And this happens for everything initially because everything's going to be in the same container. So that's the first thing that's going to happen. The second thing that happens is we're going to end up having a shift. And so we're going to shift to reach equilibrium after that dip. So we're going to have a decrease in concentration. Then we're going to shift. And what happens is we shift according to the number of moles. So this little feature here helps us understand which way it's going to shift. If you have more space, you're going to shift to the side with more moles. The example that they've got in this picture is very hard to see because it's quite small, but let's say 2A in equilibrium with a B. That's essentially what it is. And so the A are the red ones and the B's are the green ones here in these pictures. So this is an example of the volume increasing. Basically, remember, equilibrium is trying to undo what we're doing to it. It's used to a very small space, so it likes to be crowded, this particular equilibrium. It's used to a small space. So when I give it more space, it wants to be crowded again. So what happens is it will shift to the side with more moles, which is the A side, since there are 2 A's for every 1 B, so that it can try to be crowded again. Because that's the way it likes to be. It's trying to undo what we do. So if we give it more space, it actually wants less space. So again, more space, more moles, or more moles, more space, whichever way you want to look at it. Same thing over here. If we have a volume decrease, again, if we consider our C equals N over V, if we decrease volume, we're going to have an increase in concentration. So we're going to have everything increase in concentration initially, then we're going to have a shift. And again, this particular shift is less space, less moles. So going back to my equilibrium again, we have our 2A in equilibrium with our B. Our A's are the red dots, and our B's are the green dots. And again, what happens here is if I have less space, so it is accustomed to having lots of space. Whoops, lots of space. So so when I squish the container, I want to have more space, just like I used to. And so when I look at my equilibrium, there are 2 A's for every 1 B. If I have more B's, I'll have more space because there's half as many B's in this equilibrium. So you'll notice there's more green dots down here too. Okay, so that's how that one works. It's a little bit tricky. So let's see if we can work it out for ourselves. So we're going to try a decrease in volume. So the first thing that would happen if we consider our C equals N over V, if I decrease my volume, what's going to happen to the concentration? The concentration will increase for everything. Let's talk about the second part. Which way will it shift? So let's have a look at our equilibrium. On the left-hand side, we have 2 moles of ingredients. And on the right-hand side, we have 1 plus 3 for a total of 4 moles of ingredients. So we just decreased the volume, which means less. Ooh. Getting a little out of control here. Let's try that again. Less space. We want less moles then, because we're used to having a fairly large amount of space, and we're decreasing that space, so we're trying to uncrowd ourselves. So less space, less moles. That means we're going to shift to the side with less moles. We're going to shift to the left here to get to that side. On a graph, this particular type of change is spikes. It's spikes initially for everything, and then a gradual curve after that to reach equilibrium. So you'll see spikes for everything. I'm going to enforce that right here. All ingredients. So we've seen the word spike before on a graph, and that was for concentration, but concentration is just one spike, whereas all the gases are going to be affected the same way by C equals N over V. So you'll see spikes for everything. On the graph here, we have 2 up spikes here. And this is concentration, so let's just practice this on this graph. If we have 2 spikes going up, A and AB are both increasing in concentration, what happened to volume? This is a really easy mistake to make because we see up spikes and we think up volume. But remember, the graph is showing us the C. So what we're seeing is the increase in C, which means there must have been a decrease in volume. A little bit tricky there. We have 2 changes that are not affected by equilibrium, and the first one is adding a catalyst. So adding the catalyst lowers the EA. Remember, EA is actually written like that. And the EA, remember, is the sort of hill that the reactants have to climb. So if we think of our graph like this, you've seen this guy before, reactants becoming products. Going back to, again, Unit 1, this is our activation energy, the hill that the reactants have to get over to become products. So in an equilibrium reaction, remember that everything goes in 2 directions. So the reactants want to go over the hill to become products. Products want to go over the hill to become reactants. If I add a catalyst, what I'm doing is I'm lowering that hill. So reactants and products are both getting an advantage. They both have a smaller hill now, and so both of them will still maintain the same ratio, same equilibrium, but because the hill is smaller, they'll be able to reach equilibrium faster. So it doesn't affect the equilibrium. It doesn't play favorites. Reactants don't have a bigger advantage than products. They both get an advantage. So equilibrium will be the same, but we'll get there faster. The second thing is adding an inert gas. Inert just means unreactive. So think of our noble gases here. And again, if we have a bunch of noble gases that we shove into a reaction, really nothing happens. The equilibrium doesn't react with them, so nothing really happens. We might increase the number of collisions. We might reach equilibrium faster, but that would be the only outcome there. So a few questions to try for homework. We're going to focus mostly on the predictions today, and then tomorrow we'll focus more on the graphs, and then the next day we'll practice, and then you're going to do an activity at the end of the week, and you can do that alone or with a partner.